Good afternoon, everybody. Today we are going to be talking about a totally different thing. Up till now, we've looked at a variety of loads without really looking at where they actually come from. Although right in the beginning, I did talk about and along the way, I've talked about some practical situations where specific loads are seen. Today, we are going to be looking at earthquake ground motions and the response analysis of single degree of freedom systems for earthquake loads. So, we are going to be looking at Okay. So, this is what we are going to be talking about. Now, before we start talking about the response analysis, it is always a good idea to have some clue about the background of what exactly is an earthquake load. Okay. Typically, what happens is you have all over the world, because of specific fracture zones which are known as faults, always certain plates, the entire world is made up of plates, different plates, and these plates are actually floating on molten magma. So, because of certain stresses, etc. For example, to give you an idea in the Indian context, what's happening is, why are the Himalayas so high? They are so high basically because you have the Eurasian plate sitting here and you have the Indian plate which is going under the Eurasian plate and pushing it up, okay, and that is how you get the Himalayas. Okay. So, essentially what's happening is, the Indian plate is going under the Eurasian plate. Now, this junction between the two plates is called as the fault. Okay. So, what we have in India, it is called the main boundary fault. The main boundary fault is something that runs west to east along the the Terai region, all the way from the western part as west as Himachal Pradesh, all the way through the top of Uttarakhand, all throughout Uttar Pradesh, through Bihar and all the way through Assam and up into Burma. And then that plate again comes down through the parts of the Bay of Bengal, through the Andaman and Nicobar and into Indonesia. That is the zone of the fault line, large zones, right? Yeah. So, now what happens is, typically you have rocks, and as the plate moves, for example, the Indian plate is moving under the Eurasian plate at a rate of approximately about 5, and on an average about 5 centimeters a year. So, what's happening? Due to this movement, the plates are moving, but on top of the plates are rocks. So, as the plates move, the rocks are subjected to stress, okay? And of anything that it can take a particular amount, there's as it's moving, there's strain, and due to that strain there's stress. The stress build up and suddenly you have a fracture. Okay? When the fracture happens, okay, that's the earthquake. So, essentially the fracture event is the earthquake, okay? And due to this sudden jerk and release of energy, okay, you have waves propagating through the the geological rocks, and then onto this, the soil, and that's what we feel at the top. Now, in the beginning, okay, there are various kinds of waves that are developed. For example, the fastest waves are known as the longitudinal waves, the P waves. Okay, they are the fastest propagating waves, and they pretty much are the first ones to hit at a particular site. They are the first ones to hit. Although, by and large, by the time it comes to the surface, okay, it's a fairly complex thing, but if let us assume that it is a homogeneous body, then the fastest travelling wave is the P wave. Post the P wave is what is known as shear waves. Okay. Shear waves, P waves are what? Longitudinal waves are waves where the particle moves in the direction of the propagation. Shear waves are where the wave is travelling in this direction, but the particle is moving in the transverse direction. Those are known as shear waves. Okay. Shear waves are the next fastest waves and the next ones to arrive, and then we have the surface itself starts undulating, and you have Rayleigh waves and Love waves and all those kinds of other kinds of surface waves that hit, and they are the slowest propagating thing. So, if you look at a particular ground motion, okay, this is although this is a time history at a station called El Centro during the 1940 Imperial Valley earthquake. This is an El Centro station. So, that is where this record was done. So, this is the part when the P waves come. This is when the major horizontal shaking, this is the horizontal ground motion. North south ground motion is essentially the horizontal ground motion of, and this is how it looks. So, you basically have a very small part, then you have a slow build up, then it kind of then it slowly builds up, it starts shaking, and then you have a period of intense shaking, and then less shaking, and then slowly the shaking dies out. Okay. So, this is how a typical ground motion, and this is the acceleration of the ground, this is how it is measured by an accelerometer, and this is how it looks. And if you really look at it, this is the same one. This is the full shaking that was seen at the station, and this is really these parts are something that a structural engineer is not really interested in. We are really interested in the strong motion part, and the strong motion part is approximately about 30 seconds. So, this same thing, just this part has been zoomed up, and it gives you a better idea of how the shaking occurs. Okay. So, if you look at it, it starts, then it builds up, and then you get the peak. The peak ground motion in this particular case was 34% of g, which basically means 3.4 meters per second squared was the approximate ground motion that you had. And then you get motion, and then so the peak ground motion happened about 2.5 seconds into the motion. Now, that can vary, but typically if you look at it, the strong motion part stays about 15 odd seconds, and then it starts going down slowly, and this is really the surface waves coming, and that is it. Then you start getting very, very low g values, and you do not really worry about it. So, that is how a ground motion looks, and this is the ground motion that we are interested in. And so, if you look at this, this was the horizontal ground motion, and so if I plot this for a single degree of freedom system, this is how it looks. So, here I have my single degree of freedom with its foundation, right, and the foundation is, this is how a typical single story. And what is the ground motion? The ground motion is essentially this motion. So, in other words, the earthquake when it comes, okay, actually earthquake is fairly complex because it is a 3D dimensional. There will be two kinds, the ground, it will shake in this direction, it will shake in this direction. There will also be vertical shaking, but let us just look at unidirectional shaking for now, because this is the simplest kind of situation. And this is what is given as the acceleration time history, and this is the time history that we have over here that we are looking at. So, this is u double dot g. Okay. So, if you have this, right, and you have, so this equation looks like this then, right. You see, let us look at inertial reference system. So, this is an inertial reference system. Now, at a particular instant of time, the ground itself, the base, that is, the base itself will have moved by a particular amount u g. Okay. Now, due to the ground motion, this will not this way, this will have moved this much, and this will go like this will have moved this much, and this will go like this. And so, essentially what you have is, due to the ground motion, you have one part which is u g, okay, which is the inertial reference system, which is the undeformed reference system. You have u g, and on top of that you have u, which is the deformation of the. So, if you really look at it, the acceleration that this mass m sees is m u total plus c u dot plus k u is equal to 0. This becomes the equation of motion for this particular structure. And again, this is something that we have already developed last time. And so, here if you really look at it, what we have is the fact that u total is equal to u plus u g, u dot total is equal to u dot plus u dot g, and u double dot total is equal to u double dot plus u g. So, if we substitute this and write this in terms of the deformation, then this is the equation that you get. Okay. Of course, the other way of looking at it, if you really look at this, basically this part is your P of t. Okay. The other way to write it, again in terms of the total, is this is the other way to write the same ground motion. This is a lateral ground motion, and so therefore, these are degrees of freedom, are the lateral degrees of freedom. Okay. So, therefore, either one of these are valid, but this is the one that we typically use. Why? Why do we use this one? Because remember, I had said that we use this one where we are really interested in Ku, the force, the equivalent static force that is occurring due to the earthquake. So, therefore, this is the equation that we normally look at. So, looking at that particular equation, then what do we get? We get that m u dot plus c u dot plus k u is equal to minus m u g. Okay. And considering the Duhamel integral where this is p tau, what happens then? Then if you look at it, the solution u of t, the Duhamel integral approach, is equal to 1 upon m omega d 0 to t, and the p of t is minus m u g tau, that is p of tau, okay, into exponential minus xi omega t minus tau sin omega t minus tau into theta. Okay. So, this is u of t, and if I rewrite this, the m goes out, minus goes out, this becomes the following: u of t is equal to minus 1 upon omega d 0 to t This is the response of this thing. And if I really look at it, if I look at u max, the maximum value of the deformation, this is, remember this, we call this either the deformation, or we call it as the motion of the mass relative to the ground. Okay. So, this is either deformation. So, if we look at maximum deformation is nothing but over the total duration of the earthquake. Okay. So, we find this out, and whatever is the maximum value, okay, over the duration of the earthquake is the maximum deformation. Okay. So, of course, do we evaluate it this way? Well, not quite. Okay. Now, let me do something. Let me just go ahead and try to define, do this for an undamped system. There is a reason why I am doing this for an undamped system, just humor me. So, then your u max, u of t for an undamped system is going to be equal to 1 upon omega 0 to t u g tau sin omega t, sorry, this omega d becomes omega tau sin d. This is the undamped system response. Okay. Undamped system where xi is equal to 0. Okay. So, now let us try to differentiate this with respect to t. What do we get? We get u dot is equal to 1 upon m. Now, let us look at this sin omega t minus tau. Okay. If you really look at it, okay, this is going to become equal to 0 to t tau, okay, cosine omega tau, sine omega t, d tau, and okay, and minus, by the way this is minus, so this is minus, this becomes plus 1 upon 0 to t sorry, this is not u dot, this is u, u dot g t, then you have sine omega tau cosine omega t d tau. Okay. Again the sine omega t and cosine omega t comes outside, and so when we do, this is not u dot of t, this is just u of t. Okay. U dot of t basically becomes the following, minus 1 upon omega, and note that this omega becomes outside. So, this becomes omega 0 to t and this becomes cosine omega tau, and this becomes plus the cosine omega t, this becomes minus omega upon omega 0 to t and this will become sine omega tau sine omega d tau. Okay. And okay, so if you look at this, this is nothing but equal to 0 to tau okay, and u double dot, if you notice, is going to be equal to omega 0 to tau, again minus. So, this will become plus omega u double dot tau sine omega t minus tau d tau. Okay. Now, the question then becomes that if you look at it, if you look at peak, if you look at the peak, if this gives you u max, look at this one, u double dot max is nothing but equal to omega squared u max. Okay. Now, if we look at, so therefore, if xi is equal to 0, but note that u dot max is not equal to omega into u max. Why? Because if you look at this, this has cosine. So, cosine cannot be. So, even for xi equal to 0, u dot max is not equal to omega, but u double dot is equal to omega. Of course, when e to the power of minus I comes in, it becomes a little bit more complicated, and we can't I mean, I don't want to get into those details right now, because those are not of relevance. Okay. Now the question then comes back, if I go back to the original equation and the original Duhamel integral, it is the m goes away, it is 1 minus omega d 0 to t u tau e to the power of minus xi omega t minus tau sine omega d t minus tau d tau. So, if you look at this, what does u max depend on? Of course, it's u max. I'll define this as, what does this depend on? It depends on omega xi, and of course, it is a function of but if given this, if you are given this is a function of omega and psi. This is just a function of omega and psi and nothing else. Nothing else. No other. If you look at omega d is also a function of omega and xi. So, omega xi, omega d is xi, and the only other term that you have is this. So, given u max is a function of this. And so, if I plotted this as a function of omega and s, this is known as deformation response spectra. Why spectra? Well, the way this deformation spectrum is plotted is that it is a function of omega for different values of xi. That is how the deformation response spectrum is plotted. And if we look at this, then for the L centro ground motion which I had shown here, if we solved this and got the peak values. So, therefore, and if you look at this, it is a function of omega. In other words, it is also a function of time period and omega, right? Omega and time period, and typically, one way of plotting it easily is with time period, where this time period actually refers to the fundamental, the time period of natural vibration of a structure. So, this is the time period of the structure vibration, and if you look at this is the displacement, and so over across the time period for different values of xi is the spectral deformation, or the deformation response spectrum for the L centro north south ground motion. So, this is for a particular ground motion. This is how it looks. Something very, very interesting comes out of it, and that is that what we see is the following, that if you look at S d omega and psi, let us look at a structure, and it is and where the ground motion happens here, this is the structure. So, I mean S d or S d t and xi. So, let us assume, let us look at a very rigid structure, very rigid. If you have a very rigid structure, what does that mean? Omega tends to infinity, t tends to 0. Now, think of it, it is a very rigid structure, it is not being allowed to move at all. What would the deformation be? Let us look at it. This is vibrating, but this is a very rigid structure. So, what is going to happen to this? What is the deformation? deformation occurs in this. Now, if it is very rigid, what is happening? This is rigid, right. If it is rigid, this cannot deform. So, if it cannot deform, so what is my deformation, the peak deformation equal to? It is equal to 0. Look at this. As time tends to 0, okay, at time t equal to 0, the displacement is 0. This is irrespective of what your xi value is. Do you notice? Okay. Let us look at another part, and that is, let us look at a very, very flexible structure, okay, and let us look at S d as a function of t and xi. Okay. So, if we look at this, and I have a very flexible structure, a very flexible, very flexible. What does that mean? Very flexible implies that omega tends to 0 and t tends to infinity. What happens? Let us look at this. This is extremely flexible. As this moves, what is going to happen? The inertia of this is going to keep this here, and this is what is going to happen. So, what is the peak deformation? The maximum deformation. If we look at the maximum deformation, this does not move. Why? Because this is infinitely flexible, right? Infinitely flexible. So, as this moves, you know, the mass has inertia, right? And the ground motion is actually not being transmitted because these are so flexible, they cannot transfer any force. So, this is what is going to happen. As far as the mass is concerned, it does not see. So, what is the peak motion? The peak displacement, peak deformation is going to be what? This is here, right? So, peak deformation. Peak deformation is going to be equal to the peak ground displacement. Okay. Again, this is for all xi. Okay. This is for all xi. And if you look at this here, this is of course only 5 seconds. If you keep going, you will see that both of these are converging to a certain value, and that value is of the order of about 200 millimeters, because that was the peak ground displacement. 2 meters, okay, was the peak ground displacement in the El Centro north-south ground motion of 1940 Imperial Valley earthquake. Okay. So, you see, the deformation spectrum has a specific form characteristic that it has, which is very, very interesting, and that is that it does not, it has specific characteristics. For example, at time t equal to 0, S d will be 0. So, if S d is not 0, there is something wrong, because by definition, if you have a very rigid structure, that structure cannot deform. So, if you cannot deform, U max, which is a deformation, peak deformation is obviously 0. Okay. And if it is extremely flexible, that means t tends to infinity. Okay. Again, if it is extremely flexible, the ground can vibrate, the structure does not even know that the ground is vibrating, because the columns are so flexible they do not transfer any load. So, what is the peak value of the deformation? Well, whatever the ground, the maximum ground deformation is going to be the maximum deformation of the column, because the base is moving, and since the the mass stays where it is, obviously the peak deformation is going to be the peak ground displacement. Okay. So, these are aspects that are very, very important. Now, what about in the middle? Okay. Well, it is not, it's not very easy to say what is happening in the middle. Obviously, you can see that in the middle there is some kind of resonance, because if you look at it, the ground ground displacement is about 200, the peak displacement that you have is about 400. So, there is some dynamic behavior, obviously there is a dynamic behavior. Okay. This is about 3 seconds. Okay. So, that is okay. I mean, there is nothing more we can say about the deformation response spectrum. Okay. So, deformation response spectrum is a very, very important part. Okay. Now, let us look at certain other points which are important from the perspective. What are the other things that one aspect I am interested in is Umax, okay, but Umax per se does not interest me. What interests me is the following. Let us look at this. So, this is the mass and I am looking at its deformation, and so its deformation, what you have here is Ku, and that is the shear that is being transmitted to the base from the structure due to the ground motion, and that is a very important parameter. And so, this parameter, which is the elastic force, so I will call it as the elastic force peak, is obviously equal to K into Umax. There is nothing wrong with that, right. Okay. Now the question then becomes is that, okay, so this is equal to K times S d, which is a function of omega and psi. Now, can I put K, I know, is equal to m omega squared. So, if I take m omega squared S d, okay, what is the term omega squared S d equal to? What are the units of this? This is millimeter, okay, and omega squared is radians per second squared. So, this becomes millimeter per second squared. It is units of acceleration, okay, and this is called as S a, which is also a function of omega and psi. And so, if we call this, then F s max is equal to m into S a, and this is also equal to the peak base shear, which is equal to m into S a. Okay. So, what is this S a? The S a is related to the deformation spectrum, and in a way force is equal to mass into acceleration. So, it is like a pseudo acceleration, because it does not represent the true acceleration. The only case where it represents the true acceleration is, if you remember, we looked back at that particular function, didn't we? We looked back and we saw that when you have 0 psi equal to 0, the peak u is equal to omega squared into d. Okay. So, in a way the pseudo acceleration, okay, the pseudo acceleration is equal to the actual acceleration, total acceleration, okay, if psi equal to 0. Only for psi equal to 0 is the pseudo acceleration equal to actual, otherwise it is not. However, it's the pseudo acceleration spectrum is actually more important to us, because what does it do? It actually represents, if you look at this, this gives me the equivalent force that is applied to the structure okay, that is applied to the structure due to the ground motion. So, in other words, I have made the ground motion, you see the earthquake ground motion has been transformed, okay, through a specific form of the response spectrum into a mass into acceleration kind of. So, the load is due to mass into acceleration, and this of course acceleration is a pseudo acceleration, and if you draw it with respect to omega or t, okay, then this is what it looks like. If you look at the pseudo acceleration spectrum, this is what the entire thing looks like, the pseudo acceleration spectrum. Okay. There are certain interesting things about this. Is of course again the same thing, this is across all time periods, and this is where you have taken the peak one and shown it, blown it up and shown it here. So, this is the same thing, excepting that I am really taking this part and showing it a little bit larger. Okay. And this is something very, very interesting, and that is that the acceleration has a specific role to play. Note that this is the pseudo acceleration spectrum, across time period for different values of xi. Okay. So, now the point becomes that you see the earthquake ground motion, the mathematics has been left behind, and what we have seen is that it essentially becomes a problem of where, well, if you are looking at it purely from a peak perspective, the peak force in the columns and of course on the base is equal to mass into a pseudo acceleration value, which given a structure, if we look at this, so therefore, this becomes the following, that suppose I had a 1 second structure and it was 5% damping. So, okay, so no, let us look at it here. Okay, 0.4 second time period, 0.4 second time period is 2.5 hertz. Okay. So, if we look at this 0.4 second and I have a xi of 5%, I come over here, look at this value, look at this value, this is 0.6 g. So, 0.6 g. So, therefore, the peak ground acceleration becomes m into 0.6 g. So, that is 0.6 times the weight of the structure. So, that means I know that the force due to the L center ground motion is equal to the lateral force is equal to 60% of the weight of the structure. I did not have to do, I immediately know this. I did not have to do any computation, I did not have to do any structural dynamics, I did not have to do anything. So, in other words, if we have for a particular ground motion, if we have the pseudo acceleration response spectrum, we can directly get the forces that the structure is subjected to directly. I have just done it, for a particular. So, this was for a 0.4 second structure with 5% damping, and the force is 60% the weight of the structure. Very interesting. The response spectrum and its use gets highlighted through this procedure. Okay. Now, again, just like the way I tried to get your for the displacement, let me look at a situation where I want to look at what happens to the pseudo acceleration response spectrum in the limits. So, in other words, I have so it is given by a certain t and xi. So, this structure is defined through some t and xi. So, let us assume that it is very rigid. Okay. let us look at this. What happens? Okay. When it is very rigid, the base is vibrating, this is vibrating with it. Why? Well, because if it is very rigid, there is no deformation. Okay. So, therefore, if you look at it, what is happening? The top is moving exactly as the base is. So, in other words, what does S A become for very rigid? As t tends to 0, S A becomes the same as okay. This is when it is very rigid. Okay. S A becomes equal to u g max. Let us look at this. Let us come back here. At t equal to 0, what is the value? If you read it off here, you will see it is equal to 0.33 g. Let us go back. You see this? It is 0.33 g. That is the value at this point, 0.33 g. Okay. So, in other words, we have satisfied ourselves that if you have a very infinitely rigid structure, S A is equal to, and this is not a function of, this is for all xi, and this you note, you will see here is that irrespective of 2% or 5%, in this zone it goes to 0.34 g. So, that is something that is very interesting. That means, the 0 time period pseudo acceleration spectrum is equal to the ground acceleration. Okay. Let us look at a situation where you have the same structure. Now, it is given by certain t and xi, and I say it is very flexible. Very flexible means t tends to infinity. Okay, very flexible, t tends to infinity. What happens here? When it is very flexible, this is moving, this is not moving, right, because it is very flexible, none of this motion is getting transferred to the mass, and so therefore, what is S A equal to? S A equal to 0 for all xi. Well, let us look at this. You see this? It tends to 0, and irrespective of what percent of xi that you have. Okay. So, in other words, so therefore, this form is such that this is going to be u g, the peak ground acceleration, and this is going to be 0. In between, well, we will see how the thing happens. Okay. There are certain characteristics that we will look at a little bit later. Now, so I have talked about, I have given you a reason for the deformation spectra. Deformation spectra is S d omega or t of xi, okay, and I have looked at the pseudo acceleration spectra, which is S A either omega or t, function of omega or t, and psi. These two are things that we have looked at. And finally, there is the pseudo velocity spectrum. And where does that come from? That is called S v omega t, and S v is equal to omega S d, which is equal to 1 upon omega S A. okay, because obviously this thing. So, SV, what does SV have a reference to? SV, if you really look at it, let us look at this, and that is that if you have U max, okay, displacement, I want to find out the strain energy, the maximum strain energy stored. What is that equal to? Half k into U max squared. Do you agree to this? Okay, that is the maximum strain energy stored, and so this is equal to half k S d squared here, right? And what is k equal to m omega squared S d squared. So, I will call this as half m omega S d squared, and this omega S d I will call as S v squared. Okay. And so, now what are the units of S v? Obviously, velocity. What is the maximum strain energy? It is equal to half m into the pseudo velocity spectrum. So, think about it. This looks like maximum strain energy is equal to maximum kinetic energy. It looks like a kinetic energy term, does not it? Excepting that it is not kinetic energy, because it is a pseudo velocity spectrum. So, in other words, the what is SA required for? Because F S max is equal to m into SA. What is SV? SD of course is directly, I know what SD is, the maximum deformation, and the maximum strain energy is equal to half m SV squared. So, we have now defined that in terms of, for an earthquake, we can define the earthquake either by its time history or by its deformation spectrum or its velocity spectrum or its acceleration spectrum. Note that all these three are related to each other. So, any one of them is good enough for me to find out the other. Typically, what we give is, this is what we give, because here there are some specific things which I will talk about in the next lecture, which give us certain aspects of. So, therefore, either the time, so the definition of ground motion, either the time history of the ground, acceleration time history of the ground motion, or the response spectra of the ground motion. Okay? So, that is what we have talked about, and once we have the spectra, the reason why the response spectra are better is because we directly can find out response of a single degree of freedom system to earthquake loads directly from the response spectrum. Thank you very much.